warahmatullahi wabarakatuh and salam sejahtera. So this is example number 2. Laminar boundary layer on a flat plate. A uniform free stream of speed V flow parallel to an infinitesimally thin semi-infinite flat plate as sketched in this figure. So this is flat plate. The coordinate system is defined such that the plate begins at the origin. So this is y-axis, this is x-axis, and the flow is flow from the left to the right. Okay. Since the flow is symmetric about the x-axis, only the upper half of the flow is considered. Calculate the boundary layer velocity profile along the plate and discuss. So we are about to calculate the boundary layer velocity profile U as a function of x and y as the laminar boundary layer grow along the flat plate. Our assumption is first, the flow is steady and incompressible and 2D in xy plane. Number 2, the Reynolds number is high enough that the boundary layer approximation is reasonable. And number 3, the boundary layer remains laminar over the range of interest. So this problem is about laminar flow, where the Reynolds number is less than 5 multiplied to the 10 to the power of 5. Okay. So for the solution, step number 1, solve for the outer layer by ignoring the boundary layer. We know when the flow is passed over the flat plate, then the boundary layer will develop. Okay, so we know between the boundary layer there is a inviscid flow and viscous flow. So from here we can see that the flow at the inlet is equal to the flow at the outlet. So we can assume that outer flow is equal to Ux, means that flow at the x-axis is equal to V and it is constant. This is equation number 1. For the second step, assume that boundary layer is so thin. So we consider that boundary layer is so thin that it doesn't affect the outer flow solution in step 1. Next step, solve for boundary layer equation from equation 1. So this is equation 1. Okay, Ux is equal to constant. So when I differentiate this equation, okay, and this is constant, therefore I get du over dx is equal to 0. So it means no pressure gradient terms remain in x momentum boundary layer equation. So for flat plate, we can say that there is 0 pressure gradient boundary layer. Next, the continuity equation for boundary layer, del u over del x plus del v over del y is equal to 0. This is continuity equation. Next is momentum equation in x direction. U del u over del x plus v del u over del y is equal to v del square u over del y square. This is equation number 2. And we have 4 boundary condition. This is boundary condition number 1. U is equal to 0 at y is equal to 0. This is at the near the wall. Okay. Next, boundary condition number 2, when u is equal to uniform flow as y is approaching infinity. Number 3, boundary condition, u is equal to 0 at y is equal to 0. And number 4, when u is equal to uniform flow for all y at x is equal to 0. This is assumption number 3. Okay, this equation, okay, we already discussed in our previous lecture, which is Blasius exact solution, and we know this equation eta. Okay, so what is eta? Eta is y. This is square root u over viscosity multiply with x. This is equation number 4. And we have f prime. What is f prime? F prime is the ratio between local flow over uniform flow. This is equation number 5. So for step number 4, calculate quantity of interest. So we have several quantity of interest here. Okay. First, we want to calculate eta. Okay. So from our previous discussion, we already looked at this table. Okay. This table have a eta, f double prime, f1 prime, and f. Okay. So for local U over uniform flow is equal to 0.99. If we look at this table, it is at eta is equal to 5. But to be accurate, okay, we consider that the eta is 4.91. This is I get from the textbook. Okay, so from equation number 4, okay, we replace y with boundary layer thickness 4.91. Okay, in our previous discussion, we put eta is equal to 5, right? But we follow the textbook where eta is equal to 4.91. Okay, and eta, alright, so 4.91, okay, square root u over viscosity x, and we get, okay, delta over x. Okay, this one I change. Alright, okay, 4.91, this is eta is equal to square root u over viscosity x multiply with y. I replace with delta, so I modify this equation to delta over x is equal to 4.91 over square root of Reynolds number. Okay, that is for eta. Another quantity of interest is tau. Tau is shear stress. So if you still remember that I mentioned you in a previous class that eta is kind of friction. Okay, so the equation of eta is given as a viscosity. This is dynamic viscosity del u over del y at y is equal to 0, which is here. And knowing that the differentiate between this will give you f double prime. Okay, at eta is equal to 0. So if you refer table when eta is equal to 0 for f double prime, the value is 0.33206. So 0.332. Okay, then I put the this figure. Okay, I put this figure here. So this equation will become tau is equal to 0.332 rho u square over square root Reynolds number. So if you get confused, okay, please refer into Blasius's exact solution in our previous class. Okay, this is the second quantity, and our third quantity of interest is local friction coefficient of a flat plate, which is CF. Okay, and CF is given as tau over half rho u square. Okay, and the value is 0.664 over the square root of Reynolds number. Okay, step 5. Okay, since we have the equation here, tau, CF, and eta, now our last step is we need to verify that the boundary layer is thin. Consider the practical example of flow over the hood of your car. This is the example, okay, of the hood of the car while you are driving downtown at 32 km per hour on a hot day. The kinematic viscosity is given here. We approximate the hood as a flat plate of length 1.1 meter moving horizontally at a speed of 32 km per hour. So I convert this velocity into meter per second, and from the calculation I get Reynolds number as a 5.8 multiplied 10 to the power of 5. So from this equation, they still consider that this value is still in laminar. Then we continue with the boundary layer thickness. From the equation, okay, boundary layer thickness is given here for 0.91 x over square root of Reynolds number. So this Reynolds number I put at this equation and I get the boundary layer thickness as 0.71 centimeter, and it is so thin. Okay. By the end of the hood, the boundary layer is only about the quarter of an inch thickness, and our assumption of a very thin boundary layer is verified. Thank you.